Hello, this is Mr. McMurray, and welcome to a bright and wonderful Tuesday morning. It's about six something, but anyhow, way too early to be up doing this, but that's all right. Hopefully, you're here later. All right, we talked about all the physical properties and physical changes and so forth. Now we want to talk about phase changes. All right. Phase changes mean you're changing from one phase to another. If you remember, the three phases are solid, liquid, and gas. All right. So let's talk about those. First of all, start with melting. If you have a solid has atoms that are close together. They can just barely vibrate in place. If you hit them, if you add energy, so first of all, notice you have to add energy, all right, to it. Then the atoms will start to move faster. We said they can slip around each other and they become a liquid. All right. And we would call that melting. All right. Now, if we keep heating them up, eventually they not only melt. Just a second. Oh, I should check my notes. I think the next time we go back the other way. All right. If we go back the other direction, if we have a liquid and it loses energy, then once again the atoms can quit sliding around each other and get locked into place. Okay, and become solid again. Now, normally we would call that freezing. However, technically that gets a little confusing because anything that is a solid in the environment around you right now, if you're sitting on a plastic chair, for example, if you were in your desk, that plastic would be frozen because it would be below its melting point. Okay, the iron, the steel, the metal, and the legs and the basket of the desk would also be frozen. Normally, though, when we say the word frozen, we're really talking, or freezing. If it's freezing outside, we're talking about it's cold enough to freeze water. But keep in mind, everything has a different freezing point. And so sometimes they're freezing, since that has a idea of being below the freezing point of water, we just call it solidification, or it becomes solid. Okay? Now, we can also go we can go from a liquid to a gas. All right? And that would be called evaporation. Evaporation is just the process of making a vapor or a gas, so that makes sense. Or boiling. All right. Now, are those two things exactly the same thing? Well, yes and no. In both cases, you have a liquid which gains energy and becomes a gas. But if you think about it, if you have your dog's water dish outside, over time it will evaporate over the summer and it will eventually be empty. All the water will disappear. And yet, at no point did it get up to 100 degrees Celsius or 212 degrees Fahrenheit, which is the boiling point of water. Okay? And so it didn't ever reach the boiling point, whereas we know like something has to reach the melting point to melt. It doesn't have to reach the boiling point to disappear and turn into a gas. How does that happen? Well, here's the deal. Boiling is when you heat up the whole liquid, and so boiling occurs throughout the whole liquid, and you have to be above the boiling point. Okay? You stick a pan of water on the stove, and you start boiling it. Well, then it gets hot enough, then it turns steam, and you have all the steam, lots of it happening all at once because the whole pan is being heated to the point at the boiling point. And once those molecules get to the boiling point, they will start turning into steam or water vapor. Okay. Now, on the other hand, evaporation occurs at temperatures below the boiling point. Okay. And so rather than all or much of the molecules in it all being heated up at once, evaporation is more when individual molecules get enough energy to break loose, okay? When we talk about the temperature of the water, we're really taking the average temperature or the average motion of all those molecules. But there might be individual molecules that have enough energy to break loose, okay? And that's what evaporation is. It only occurs at the surface, okay? And it's below the boiling point, but individual molecules get enough energy to escape from the surface. Okay, and so therefore that is evaporation. It's much slower because there's only a few molecules at a time. And just for the record, it also has to do with air pressure. Okay, if you can lower the air pressure, things will boil at lower temperatures. Okay, or they will turn to a gas at lower temperatures, and you'll have higher evaporation. But we won't get into that right now. But just know that. So evaporation is when individual molecules get enough energy and escape, but it only occurs at the surface. So if you want a lot of stuff to evaporate, you need a large surface area, a flat surface area. Okay, if you put water in a glass, it can only evaporate off the surface. If you pour the same water out into a plate or a pie tin, it's going to evaporate faster because there's more surface area where things can evaporate from it. All right. Now, the opposite of that would be condensation. If you have a gas that loses energy and becomes back into a liquid, we say it condenses. Now, part of the reason we say that it condenses is because it takes up less space. Gases, if you remember, once they bounce around, they spread out and are constantly moving around, so they really spread out. When they turn back into a liquid, they take up a lot less space. Okay, and so that is why it's called condensation. It's condensed or into a smaller amount of space when it turns into a liquid. Whoops, sorry about that. We don't need to do that just yet. Okay, example of this would be dew. When you see dew on the grass, it got cold at night. Some of the water vapor in the air changed back to water droplets. Same thing if you have a glass of ice water. If you put ice in the glass, you start seeing little beads of sweat, but the sweat is just water vapor. It was a gas in the air, and part of the humidity or the water vapor in the air. And when it got cold, right next to it was sitting right next to the glass, as heat from the air went into the glass of water, it cooled it down. It was so cool it couldn't stay as a gas anymore. It turned into a liquid and it condensed on the outside of the glass. Okay, so those are just a couple examples of condensation. All right, now sublimation. Sublimation, we skip a step. We go straight from a solid, we gain energy, but instead of melting, we go straight to a gas. Okay, and probably the most common example people have heard of is dry ice. All right, if you have dry ice, it's called dry ice because it doesn't melt and it never becomes a liquid. It just becomes a gas and released as a water vapor. All right, now, sometimes you'll see it in plays and stuff like that when they need fog. They will use it. Fog machines usually use dry ice. Okay, now, interestingly enough, the fog is actually water vapor that has condensed. Okay, because when dry ice is carbon dioxide gas that has been frozen into a solid block. When it sublimates, it becomes part of a gas. It cools the air down so much that the water vapor in the air condenses, and so you are actually seeing fog. Okay, but anyhow, so it is actually carbon dioxide gas that they put pressure or whatever and forced it to become a solid. All right, and it goes straight from one to the other. All right, now, we don't see this much here, but you would also see the same thing. Say if you're up north where it snows, and if say we got 6 inches of snow, and then it didn't snow for several weeks, the snow would still get less and less and less every day, even though the temperature might never get above freezing. Okay, so it's not warm enough to melt it, and the ground by the middle of the winter is not warm enough to really melt it much. And so basically, it is technically sublimating. Some of that snow is actually becoming water vapor, not melting, but just going straight to that. Same thing can happen in your freezer. If I have an ice tray with ice cubes down in the teacher's lounge, if I leave it there all summer, by the time I come back in the fall, there'll still be a little bit of ice cube left, but most of the ice cube is gone. Why? Because it has sublimated and become water vapor or gas. Same way if we talk about freezer burn, what we really mean is it's drying out your food, because ice crystals in the food is actually changing from ice to water vapor, and so it's really drying out. And so when you get the food out, if it's been freezer burned, really it's all dry and tough because it's dried out basically, even though it was below freezing all the time in the freezer. All right, now could you do the opposite? Could you go from a gas straight to a liquid or solid? Sorry, straight from a gas to a solid? And the answer is yes. You don't hear about this much. Sublimation you don't hear about a lot, but deposition you hear about even less. And this is when a gas loses energy but goes straight to a solid. Okay, you may have had to scrape some of this off your windshield in the wintertime. Okay, because in the wintertime, if it gets cold enough, instead of going from water vapor in the air to dew, it goes straight to ice crystals. And those ice crystals are the frost, which is on your windshield and your windows and the trees and the grass and whatever else. Okay, that's all frost is. Technically, that's what snowflakes are. Okay, sleet is when you have raindrops that's freezing, and hail would be raindrops that freeze, and then they get bigger and bigger, more water freezing on the outside. So if it's freezing, then it would be sleet or hail. But if you have snow, it goes straight from water vapor or gases in the air into the crystal solid, and it makes snowflakes. Okay, just like the crystals on your windshield are, sorry, my brain just went dead. Are the frost basically is going from a water vapor straight to a solid. All right. And so those are the different phase changes of matter. You need to know if they gain energy or lose energy to do each of those and what each one is called. All right, now we're going to talk just real briefly about mixtures. Okay, another way that we can make a physical change is to mix two substances together. Okay, so if we mix two together, but they do not chemically combine to make a new chemical. All right, so if I take salt and sand and I mix it together, that's a mixture. Okay, it's just the way it is. Okay, they have not chemically combined. They didn't make a new salt sand or something like that. They just make salt and sand, and you have a mixture of those two things. Okay, now that is one way. The most common mixture, though, we talk about are solutions. Solutions is a mixture in which one substance is dissolved in another. Okay, and one of the most common mixtures is salt water or something else dissolved in water. Usually we think about something dissolved in water as being that. Okay, and if you look at water, which is, H2O or O2H, let me just draw. And water actually has an oxygen with two little hydrogens on here. And the reason what holds oxygen together is that, theoretically at least, the hydrogen and the oxygen share an electron. And since they're sharing it, they have to stay together. And so theoretically, half the time this electron goes around hydrogen and half the time it goes around oxygen. And same thing with, there's an electron from this hydrogen that goes around oxygen, and sometimes it goes around the hydrogen. So they're supposed to share. But you notice the oxygen is a whole lot bigger, and kind of like kids in a sandbox. If you have a big kid and two little kids and they're supposed to share the toys, guess who gets to share the toys most of the time? Well, the big boy. And so the same thing happens here. And so oxygen is normally negative, and the hydrogen side is mostly positive because they've lost their electron most of the time, and most of the time it's going around the electron. So that makes it positive and negative. So if we put something like sodium chloride in the water, NaCl, which is sodium chlorine, well, the sodium, which is positive, says, hey, I think I'll hang out over here with the negative side of the water because it's a negative charge, I'm a positive charge, I'm attracted to it. And the chlorine says, fine, I have a negative charge, I don't mind, I'll go hang out on the other side of the water. And so you have chlorine that's negative attracted to the positive side of the water. And so when you add salt to water and it disappears, that's what's happening. The sodium is going to one side, the chlorine is going to the other side, and it's hard to explain, but it's still salt, still tastes salty, but it is dissolved, okay? And so when we dissolve something, we have two parts. We have a solute, what is being dissolved, usually a solid, although it doesn't have to be, and that's a solute. So the salt, the sugar, whatever we're putting in the water. If I have iced tea, the sugar would be the solute. All right, the solvent is what's dissolving the solute. Usually we think of water or a liquid as doing that, but it doesn't have to be, okay? Let's think of this a little bit. For example, our air is a mixture of different gases. Nitrogen, about 75% of it's nitrogen. Only about 18 or 20% of it is oxygen, and you have smaller amounts of carbon dioxide and helium and argon, a bunch of other little gases that are very small parts of it. Okay? And so we would say in that case, we would say since the biggest amount is the nitrogen, we'd say it's the solvent. Okay, so we would say it's the solvent. And we would say that what the other gases that are dissolved in it are the solutes. So you have gases and gases. If you have a fish tank, you're bubbling oxygen. Well, the bubbles that come up to the top, those don't do the fish any good. But some of the oxygen is dissolved in the water. So you have a gas that's dissolved in the water. Okay? You could have liquids that are dissolved together, like alcohol and water. If you get rubbing alcohol, it's usually 70% rubbing alcohol or isopropyl alcohol and 30% water. Okay? So, basically, those are your two parts. And you can do liquids and liquids, you can do solids and liquids, you can do liquids and gases. All right, we will stop right there. That's all we need to know for now. And enjoy the rest of your day.